today, we are presenting our working model of a simple steam turbine developed using an aluminium soda can and other readily available materials. This project was designed to demonstrate the basic principles of thermodynamics through a simple and practical engineering model. Although our prototype is small in size, it represents the same fundamental concept used in real steam turbines found in thermal power plants and various industrial applications. Moving on, this project also promotes sustainability. Instead of using expensive materials, we reuse an aluminium soda can and other recyclable materials to build our prototype, showing that engineering concepts can be demonstrated effectively using simple, low-cost, and environmentally friendly materials. The objectives of the project are to develop a simple steam turbine model using recycled materials, demonstrate the conversion of heat energy into useful work through steam, enhance our understanding of basic thermodynamics, and promote sustainable engineering practices. Now, teammate will explain where this principle is used in the real world.
Our steam turbine prototype demonstrates how steam energy is converted into mechanical engineering, which is the same principle that is used in many real-world applications. This concept is commonly used in thermal power plants, biomass plants, and other steam-related based industry to generate electricity. Our prototype also represents the main component of the actual steam turbine system. For example, the turbine produces steam, the nozzle increases the steam velocity, the turbine blades extract energy from the steam, and the shaft transfers the rotation motion. In industry system, the shaft is connected to a generator to produce electricity. Although our model is simplified, it successfully demonstrates the basic operating principle of industry steam turbine.
Now let's take a closer look at the design of our prototype. The main component is an aluminum soda can which acts as a boiler. There is a small amount of water inside the can, and the can is still sealed except for a tiny pinhole that shall act as the nozzle. Below the can, we place a candle as the heat source. In front of the nozzle, we position a lightweight turbine that was made from aluminum as well. Initially, before the steam begins to escape, the can behaves like a closed system because the heat enters the system but no mass leaves it. However, as heating continues, the water will change into steam and escapes the system. When it escapes, the steam this changes into an open system because the steam will cross the system boundary and leave the control volume. The high-speed steam will strike the turbine to rotate.
Now I will talk about the operation of our steam turbine. As the candles hit the aluminum can, heat energy is transferred to the water inside through the metal surface. Initially, the water temperature rises gradually. This stage is known as sensible heating, where the temperature increases without any change in state. When the water reaches its saturation temperature at the internal pressure, phase change occurs. The liquid water starts converting into steam. The steam occupies a much larger volume than liquid water, causing pressure to build up inside the can. This high-pressure steam exits rapidly through the small pinhole nozzle. As the steam leaves the nozzle, thermal energy is converted into kinetic energy because the steam accelerates to a very high velocity. The fast-moving steam then strikes the turbine blade, transferring momentum to them and causing the turbine wheel to rotate. So the complete energy conversion taking place in our project is from thermal energy to kinetic energy and finally mechanical energy. This is the same principle used in actual steam turbines for electricity generation.
Now, for the calculation of our prototype, for our setup, we use 40 milliliters of water, which equals 0.04 kilograms, heated by a single candle, providing an assumed 80 watt of heat input. The exit nozzle was punctured using a 2 mm stick, giving us a cross-sectional area of 3.14 times 10 to the power of -6 square meters. Using the standard steam tables at atmospheric pressures, we evaluate liquid water and steam properties at 100 degrees Celsius. First, we calculate the total thermal energy required, a sensible heat Q1, to raise our 40 milliliters of water from room temperature to boiling point, is 12.55 kilojoules. Next, the latent heat Q2, needed to completely vaporize the boiling water into steam, is 90.26 kilojoules. Adding these together gives a total thermal energy requirement of 102.81 kilojoules. Second, we calculate the jet velocity and power output. Based on our 80 watt heat rate, the time required for vaporization gives us a steam mass flow rate of 3.55 times 10 to the power of negative 5 kilograms per second. Applying the continuity equation with the steam density of 0.6 kilogram per cubic meter, the exit velocity of the steam jet forcing its way out of the 2 millimeter hole is 18.8 meters per second. Finally, this high velocity jet produces a theoretical kinetic power output of 0.0063 watts, directed straight at our turbine blades to create rotation.
I'll be explaining the analysis part. In total, we have applied the first law of thermodynamics, and as why is it applied? Obviously, I'll explain that first. So the candle, which is a chemical energy which produces heat, and then the heat is transferred to water via like a thermal energy, and water is like when it keeps on heating and when there's a change in the pressure difference and the temperature difference, the water turns into steam and exists through the nozzle. We know that the size of the nozzle is small to increase the velocity. So greater the velocity, greater will be the speed of the work output or the fan. And then when the steam strikes the turbine blades and causes rotation, which is in the end a mechanical energy. Moving on further to the performance of prototype, the energy required to convert 40 ml of water into steam was considered to be around 102.81 kj, and the steam exit velocity was 18.8 meter per second, and the calculated kinetic power output was supposedly to be 0.0063 watt, which is comparatively fine for a low-based prototype. And but at the end, right, we got the output that the turbine was rotating perfectly. Moving on further to the energy loss, obviously the energy is lost to the surrounding air. An aluminum can is not also well insulated. There's a steam leakage through nozzle, so there were different losses that we see here. And then if we compare this with industrial steam turbines, obviously this is a very small prototype, but the output is considered to be the same. That the industrial turbines operate at high pressure and high temperature, so the velocity is also greater, And our prototype is obviously a small scale and only demonstrates the first law of thermodynamics and the working of the Bernoulli's so-called equation. What are the possible improvements that we could have done in our project is that we could have added like a thermal insulation around the boiler, and we could have used like a large or more efficient nozzle, because in the initial time we faced a lot of issues for generating for the fan to move. So we could have worked on that, and obviously we could have reduced the friction via bearings. Obviously friction cannot be reduced completely, but yeah, we can minimize the friction, right? And then we could have used a stronger heat source instead of like a candle to have a better output.
To conclude, this project successfully demonstrated the fundamental principle behind the steam turbine and the first law of thermodynamics of an open system. Hence, the energy transformation takes place in 3 stages, which is from chemical energy of combustion to converted into thermal energy, which heats the water and produces steam, and then mechanical energy that moves the turbine. This process also illustrates that not all input energy is converted into useful work, and a lot of energy will be lost due to heat transfer. The efficiency of our prototype is much lower than that of an industrial steam turbine and can only be used as an example. Finally, by constructing this prototype 100% from recycled materials, we were able to demonstrate that engineering concepts can be taught effectively in a simple, low-cost, and sustainable way. Thank you.